All right. Hello, everyone. Good evening, or whatever time it is from where you're watching. And welcome to today's stream. And yeah, today I'm going to be looking at some of the challenges from the Nixu challenge. So, Nixu is a IT security company. You can read more about them on their website, nixu.com. I have mostly no affiliation with them. I know people who work there and so on, but like I'm not sponsored or anything by them. But they have created this challenge, which I think they use it as like a recruitment thing. So candidates probably might have to solve some of these challenges. Luckily, however, they release more of them over time. So without ruining their recruitment process, we can still solve some of these older ones with no issues. So I think today I will be looking at the 2019 challenges, and I will not really look at any of the recent challenges since that could probably ruin some of their recruitment efforts if there are solutions available on the internet. By the way, please let me know if there are any issues with the sound or image in the chat. And yeah, we should get going. So the idea is that we'll, as I said, pick some of these challenges from 2019. I think I have done some of these a long time ago. So in the description I said that this was like a blind solve, and it kind of is, because even though I have solved some of these before, it was so long ago that I don't really remember anything. So yeah, maybe like in some of these I might remember some detail or anything, but it is like mostly a blind solve. So first of all, let's see if we can do some kind of login. Let's see if I do have an account on this, or maybe I should create like a new one or something. Just give me a second here. Um, oh no, cool. Okay, so it seems I have not actually looked at the 2019 challenges, so we are all good. I just checked this on my other screen. So yeah, and let's just start with something. I think I will just first of all, let's increase the text size a little bit so that we can easily see. So you see they have their just different challenges here, some different categories, and so on, and the number of solves. So let's start with something simple. So let's look at this one. It's Pwnel, 100 point, 124 solvers, a device control panel. So we click this one. Okay, found an exposed device controller interface, IP and a port, and some materials. So we download those. They call this challenge just device. So let's do the same thing, create a directory, device, and we copy the downloaded file and we extract it. And we have a file with source code and an ELF binary, 64-bit binary. So in this one, it's a Pwnel, and we're given the source code. So that means we don't have to do any, or very little reversing at least. So let me just readjust some things here. Yeah, so this is the source code of the program, not like there's a little bit of stuff here in here, but 200 lines of code, and we saw something about flag 1 and flag 2. Are there like 2 parts? Let's just go back. Right, so there seems to be there's kind of like a 2-in-1 challenge, I guess. Let's check the description here. This device control panel Pwnel. Oh, it's not a panel, it's a Pwnel. The hello from Hacktivator in the chat. Hello. Welcome to the stream. Hope you enjoy it. And yeah, so this is just where you submit the other flag, and this also has like 104 solvers. Okay. So yeah, so it was a message in chat. Never heard of this channel. Mind introducing yourself? Absolutely. For any new viewers, I'm Kalle. I work with security, and sometimes I do streams like this where I take one or more CTF challenges and I try to solve them without having looked at them before. So for a lot of challenges, like these CTF challenges and stuff, you could find write-ups on the internet, and you could like read the solution in maybe like 2 or 3 or 4 pages of text, and that's very good, and you can learn a lot from that. But what it's often missing is kind of the process, how you arrived at that, what things did you try, and so on. So this is kind of that thing, like trying to provide like the full process, my thinking, like how I'm approaching these challenges, and how I'm thinking about it, what tools I'm using, and like including all of the mistakes and so on. Because I think there's a lot of value from that as well, because you typically don't go like straight to the solution. You typically have to like try a whole bunch of different things, which may or may not be correct. So yeah, this is like the main content I have here on the channel. I also have a few videos and stuff, and I plan on doing more like scripted or like edited content. I kind of made like a New Year's thing that I would generally have more gaming in my life this year, which included like making games, hacking games, playing games. So I want to do more stuff related to games. We'll see if that happens, but for now, let's focus on this. Yeah. Right. So we have a program like this, some amount of code. So let's start at the main function of this code. And this function, what it does is, this is something that you will see in a lot of exploitation challenges. By the way, I should probably actually explain this, because it's something I usually just skip over. What this does is that it turns off the buffering for the standard output buffer. And the reason you typically do this is because otherwise it can become very messy if you're trying to leak something from the binary and there is buffering, and then you would need to trigger a flush for that data to actually be sent. Like just because there's a print or a write or something in the code doesn't necessarily mean that will actually be outputted to the client until you flush the buffer, which happens in specific circumstances. But by setting like turning off the buffering, all the output will immediately get flushed and sent to the client. So this is something you typically see in like Pwnable challenge, just make the life a little bit easier and less annoying for the player. And then we have a welcome message, and then we call this read flags function, which will open these 2 flag files and store them in these variables, which I assume are like global variables. Yes, so we have these 2 global variables. And we have this value called the master, which we we don't know what it is yet. There's some device limit, some structure for device, but I guess we'll get to that. And then we have the main loop, which you have here. They print the menu, and they also have this like hidden. So I have this ID, which is some value, and then there's this hidden part of the menu that says like, if we are ID 0, show the admin options. Yeah, so the hi Activator, welcome. And this is the code you got as a CTF challenge. Yes, so this code was provided in this case by the challenge authors. So in most pwnable challenges, you only get the compiled binary, and you have to like reverse engineer the binary to get the contents and to be able to understand what the program is doing. But in these simpler or easier pwnable challenges, they focus more on the actual exploitation part, and they make the kind of like bug finding part easier by providing you with the source code. So in this case, we do have the source code. So we read a choice here, and here we can see the first bug, which is that you have this fgets call, which will read data from standard input into this variable, and it will read 127 characters, but this buffer is only 8 characters large. So here we have, this is a clear buffer overflow issue here. Now, what we can do with this will depend on a number of things. And this actually gives us good reason actually to check out the binary, because something we need to check with the binary is what security features is it compiled with. So we run this program called checksec, so check security on the compiled binary, which we were also given. And we see that it has no stack canary. So that means that we can overwrite the return address. It does have NX, it does have pi, so it's a position independent executable. So we do not know where in memory the code will be located. And this partial rel row basically means nothing in this context. There are two other options here, like no rel row, which is essentially for our purposes, it's the same thing here as partial. But if it would have said like full rel row, that's something that we would have had to take into consideration. But yeah, I can explain that at a different point, or if we get to that. But this means that we could, for example, overwrite the return address, but without having some kind of memory leak, we do not know where any of the code is located, so we can't just jump freely to other parts of the code. So let's continue. Let's keep this in mind and continue looking. So we have these choices here: list devices, add device, edit device, process. And we have a quit, and then if we are this ID 0, we can get access to the admin menu. Okay, and the admin menu is here, and we'll actually just print the flag. So the first goal here is just to overwrite this or modify this ID somehow to make us admin, to make us access the admin menu, so that we can just get the first flag printed. So yes, and let's see, is the ID actually referenced anywhere else? No, it's not. It's defined here as a local variable, and inside of this function there are only these two references, so it's never written to. All right, and let's look at the other functionality. So we have, what did we say? List devices. So we have this devices variable, which is a global variable. It's an array of these device structs and 24 of them. And a device consists of a name, a description, and an ID. So the list device thing is pretty simple. It just loops over the list, and if it until it encounters an device with ID 0, and then breaks and just prints out the ID, well, the index, the ID, the name, and the description. Pretty simple. We have the add device thing, which will create a temporary ID, which it will assign here. It will then call this input function for the description and the name, and then we'll copy those onto the struct. And the input function is up here, which will get input according to this size from standard input, write it to the buffer, and it will also check that if the last character here is a new line, it will replace it with a null byte. All right. But here we also have a buffer overflow. Specifically, we see that this description array here is 256 bytes, but then they copy it over to the struct where the description is only 128 bytes. So we have a buffer overflow here in the device array as well. So let's see. We have this edit device function, which will ask for what's this next thing? Okay, let's skip that for a second. It will ask for a choice, and then the target. Oh, so they're just subtracting. So they're just looking at the ASCII value of the first character of our input, and then next is maybe related to when we add. Let's look at add devices first, actually, before we go into edit. We did that. Okay. Next is here. It's incremented here. It's the index of the next device to add. So here, if next is 0, then we haven't added any devices yet. So we just print this and we return. If next is okay, so it's just printing. It's using this to printing out the valid range of indices that we can choose from. But this thing is a bit odd because this means that we could never choose or I mean, okay, so it's fine. It's just that we're not actually using numbers to pick the index. We're using just the ASCII value, but whatever, it will work. Same issue here, the buffer overflow. And then they have the process thing. where they so as pointed out, like if you subtract the ASCII value for 0, you get like the numerical value, which is true for the digits 0 to 9. But if I input 10, then that will be the same as just inputting 1, and we can have 24 devices, so it doesn't really make sense, but it will work in a strange way, because it will just be, if we want to pick number 10, we take the character that comes after 9, which would be like a colon, would be device 10, and so on. So I mean, yeah, it works. And here we have a reference to flag number 2. Specifically, they want to check if they process all the devices, and they check if any one of them has the master ID, and then they will print the flag. This is great. This means that we can use this buffer overflow to... So in this array here, devices, we will have copies of this struct containing name, description, and ID. And if we consider how this is laid out in memory, you can just open up new. We will just have these next to each other. So if you consider this some kind of like abstract view of the memory, you will have like 32 bytes of name of the first item, and then 128 bytes of the description of the first item, and then you have 8 bytes, it's a 64-bit integer ID, and then actually here we might have some padding to align this to a certain alignment. So this is something that we need to check. And then we will have the name, the description, ID, and then possibly some padding, and so on. And as I said, we have a buffer overflow in the description part of this. So if we write 256 bytes here, we will just first write the first 128 bytes into this description, then 8 bytes here, then maybe a few bytes into the padding, and so on. But the important part here actually is that, assuming that they are actually laid out like this in memory, after the description we just overwrite the ID, so we don't even need that big of a an overflow. But consider this scenario where the ID would be like the first part of the structure. Then we could still do this, because then we could overflow from one device down to the next device in memory. So that would also work. But then we would have to figure out if there's any padding and how big that is. But that's not very complicated. So that's a very good strategy for flag number 2. And for flag number 1, so it shouldn't be the case, but if these two were laid out in memory such that ID was after choice, then of course this overflow could just be used to like overflow from this choice buffer into the ID buffer. That's typically not how they are arranged, I think, but we should definitely check this out. So for this, let's actually use Binary Ninja, because now we want to look at the compiled program to just see how these things are laid out in memory. So let's look at this main, the main loop, and then let me switch to, can we do the, yeah, so this is the high level IL in Binary Ninja, which is almost like decompilation. Very nice. So this value here, no, sorry, that's not. Oh, so it actually looks like the ID thing has been just optimized away. So there's a question here to explain how we're going to use the buffer overflow. Is the ID, will it be next in the memory to the return address? Yeah, so this is the thing we're investigating right now. I was just saying that if the choice buffer is before, because both of these things, they will be on the stack. And either this one will be before the ID on the stack or it will be after. Now, my guess is that it's going to be after, because typically buffers like this are placed at the end of the stack frame. But if it turns out that the choice buffer comes first, then we could just overflow from choice into the ID variable. And yes, this is a decision made by the compiler how to arrange these things in the compiled version. And in fact, if we look at the binary here, it seems that something like it seems like it's missing altogether, because let's see, we would have let's see what it's doing here. This number 4 here, yeah. So there's some a little bit of there are like two things going on here. First of all, you see that the case values, they don't match with the source code. You see here, list devices is this one, the character 1, but here it's like the value 0. But then if we look at which variable they are using to switch on, it's this variable, which we could call like choice value, which is this choice buffer. I think. But here you see that they subtract hex 31, which is this ASCII value. So they are doing the equivalent of don't switch on this, but switch on this and subtract 1, and then put the 0 here, 1 here, and so on. That's what the compiler is doing here. But it's the equivalent functionality. But we can see here that, so this means that this will be number 7 in the compiled version. And we see that in the source code, it says if ID is 0, then admin menu, otherwise print you are not admin. But here in the compiled version, we can see that it's only saying, it's just printing you are not an admin. So it seems that the compiler since this ID, the compiler has detected that this ID is never written to, so it has just optimized away this whole thing. Like it removed the whole variable, and it could see that this is never true, so we just delete this part of the code, and this is never true, so we can just delete this whole part of the code. So this variable is actually neither before or after the choice buffer. It's not there at all. So this is why having the source code is valuable, but you need to check the compiled version because the compiler will do stuff to the code. So that kind of ruined that idea. But I think the other idea with the overflowing the struct should still be fine. So we can actually, let's just start, let's delete this and start writing the exploit for this. So we're using Python with Pwn tools, and we got this host and port from the challenge description. But we're going to start with developing this exploit locally. So we start this process, and then we can do this interactive. So what we're doing here is, this will be used later. We are starting the process, and then we're just connecting it to like an interactive session here in Python. So like running this. Did my Pwn tools installation suddenly break? Let me just see what's going on. I have no idea, but sure, let's just install Pwn tools again. It is Pwn tools. So it's claiming to be installed. Oh, right. This was when I was doing some FPGA tutorial yesterday. Let's get rid of that. Oh, and we will have to... Okay. Now we're good. Sorry about that. So the issue was that I had messed up my path. So there was another separate Python installation as part of a completely different software package that I was playing around with yesterday, and I didn't consider the consequences of those changes. Anyway, I reverted this. We're all good. We're running the script. Except it seems that it crashed. Let's just run the program. Okay, so the program crashes from just running it. Let's open it up in a debugger. and check the backtrace. Oh, right. It's crashing on the read flags function, of course. So because there is no arrow checking inside here, it just assumes that these files exist. So we should sort that out. We create this this fake flag and fake flag 2 in the flag. Oh, it's even called flag1.txt. So now we can run the program. Nice. And we can also run it from inside our script. Cool. And we could do like add device, name, either2, description, cool. And then like list devices. We can see the ID. See, you can process, looking for master device ID, processing done, no master device I found. All right. Now at least we should be able to fairly simply exploit the second flag and get that one. So what we will do is we will run the process, and then actually I like to create, like when there are like menus and like this to navigate, I typically create a small helper function like this. So we will want to wait until we have received this quit line, and then we want to send this choice. So in this case, first we want to create a device. So we do 2. And then what does the creation of a device look like? We actually just did this. It will say name. Actually, let's look in the code. Add the device. Here it will say name. So so we wait until this happens, and then we can just actually send an empty string because we don't really care about the name. And then the description, we want to wait for it. So what we're doing here in Pwtools is that we're kind of like creating this we're creating this script to interact with the process so that we don't have to sit here and type it out in the terminal ourselves. So what I'm doing here, I'm creating this process thing, and I'm saying like receive one line at a time and stop once you encounter a line that contains this string. So this will like just go through all of the lines until it finds this one. And then we want to send our one line of text, which is the menu choice that we want to do. And then we want to do the same thing, receive stuff until we get the line which says name, colon. And then we want to send our name, which we don't really care about at the moment. And then the same thing for description. And here, we want to figure out this exactly where part of our input ends up in memory, like which part of it affects the ID. Now we could just do this by guessing or assuming stuff. So we read this description of the device structure, and it might be the case that these 4 bytes follow immediately after these 128 bytes, but that's not necessarily the case. I mean, I think in this case, I think it definitely will be, but let's not assume that, and let's just do this nice way to figure out how we can get this very quickly. So what we will do is we will create our payload using this function called cyclic, which will create a string. I should actually run this in a terminal. Shorter one. Let's make a longer one. So cyclic will create this string which follows this pattern, which is a De Bruijn pattern. Sorry for the pronunciation. But basically what you can do with this is that you can take any, since we define now the length to be 8 bytes, so you can take any 8-byte substring of this string, take any 8 bytes here, and then you can immediately calculate where in the string this occurs. So basically what we will do is we create this cyclic string of 200 characters. We send this, and then in the debugger, we check what the device ID becomes. And then we can feed that back using the cyclic find function. And then we just get this offset calculated for us. So this is kind of a more sophisticated version of doing like sending maybe like 4 A's and then 4 B's and then 4 C's to C. This is a more efficient method of doing that. So we send this payload, and then we are done with creating the device. So then in the menu, we can go for list devices. So let's just do this. Run our exploit. And now here it prints out the ID of our first device, which is this value here. And here it has taken those 8 bytes as a hexadecimal value and printed it out to the screen. So now we can take this back into our program here, and we can change this. So we comment out this first version of the payload, and then instead we add a certain amount of padding, and the amount of padding we add is this cyclic find value. So actually we can just make this even more clear. Create this variable padding length, and then we just print this out. And then now just to try this, we can add 8 B's. So if we did this correctly now, then the ID will be exactly those 8 B's. So it will be hex 42, 42, 42, and so on. So let's try to run this again. And yes, that seems to be correct. And we see here padding length 128. So it was in fact the case that the ID came directly after the description. But this would have worked even if there was some kind of space here in between. So now let's just take this master thing and put it there instead. So payload, and then in Pwn tools, there's this convenient function to pack a 64-bit value to bytes. So instead of these 8 P's, we put this master value here, and then we send this. And then we can do process. And something didn't work. Is there a like... let's see. This was the ID that we got back. This was the ID that we were trying to set. And we see that this first byte here is not correct. So let's check the code again. If I glanced over something. When is the ID? This is the temporary ID it's set up. Then you have the description. Wait, 6B is okay, so nothing specific. I copy the value. Oh. So for some reason, this one byte is getting overwritten with the incorrect and this is, oh, right. Yes, this is because, so we have this null byte here. So this value gets packed in little endian order. So if we actually print out the payload. So here's the payload that we actually send. So here are all those A's. And then you have the bytes here. And you see that the least significant byte, AF, comes first here. And so on. And we have a null byte here. And this is an issue then. Because what do we use to read this? We use this input function here, which will use fgets. So now you check the documentation for fgets, and so reads characters from stream and stores them as a C string until this many character has been read, or either a new line or the end of file is reached. So wait, that means that a null byte should not be an issue. So here it will use strlen, which will read until the first null byte is encountered. But this will just check this value here, which is not a new line. So this thing is not important. But I guess what we could do, so I'm not completely sure why fgets, maybe it does actually stop reading at a null byte as well. But what we can do then is just to do this in like 2 passes, I think. So because when we edit a device, the ID is not modified, right? Good. So what we can do then is, when we create the device, we send the sequence of, well, whatever as the first 7 bytes, and then this 81 bytes to put that one in place. And then we do an edit and we get those other 7 bytes in place. So that would work. So instead of this, we would have, so if we do this for starters, let's comment out this. We get this value with all the 81s. So now let's just edit the device. So which is, that's number 3, device to edit 1, and then the name and the description. So we do, what did I say, menu 3, and then again, wait for the name and the description prompts. And then we basically do this again. We create the payload, have some padding that we don't care about. Then we add this correct value here. And then we send this. Are the prompts? Oh, we need to select the device, of course. Select device to edit. Let's see, lines contains, and then we send device number 1 to edit, and then it will ask for the name and then the description and so on. So we run this, and it's still hung up. So this is a good opportunity to set the level to debug here, and we can get all the. All right, so this is the mistake. We see all the conversation going on here until it says new name, but we are here waiting for it to say name. So that was a mistake. So there should be new name and new description. That's the prompts we are waiting for. And then running all of this again, it seems to fine. And then if we do process, and now, actually, first let's do list. And now we see that it has the correct ID here. So when we do process, it prints the flag. But since we're running this locally, it of course only prints this this fake flag that we created. But now let's then turn this log level down again, and then we actually try to run this against the live target. And so the very nice thing now about using Pwntools then is that we only need to replace this like tube is what they call it in Pwntools. So instead of R being a process, it can be a network socket. So we connect to the host and the port, and we just run the same thing again. And we run process, and here we get the flag. How to deal with null bytes. So we can go here and just, no, sorry, this was flag number 2. So we submit this here, and we have posted the flag. So we scored a flag. Nice. So that was the second part of the challenge. Now the question is, how do we handle the first part? Because since this seems to be kind of like a beginner's challenge, I'm I'm afraid that they have like accidentally broken this challenge by like recompiling it. So the question here, how did you get the right ID to put? Yeah, it was here in the source code. So we have this static master here, this master variable, and then we can check down here. When you run the process thing, it checks the ID of every device, and if any of them is this master value, it will print the flag. So I did this in two parts, where I first put the correct the last byte. I put the correct last byte in position because the input will terminate at this null byte. So when we create the structure, this device, we will set the ID to this 81, 81, 81, and so on. And then we edit it and we overwrite the first 7 bytes with the correct value. So we do this in 2 steps and then list it. And it says, like, could you get the right ID without the source code? Yeah, of course. Like, we could look here in the compilation and we could check. So now we're lucky that you still have like the names and stuff. But let's look here in the process thing. It would check here. And this is a bit hard to read, but here is, oh wait, so this thing. Oh, sorry. Yeah, here it is, of course. So here you would have the value here. So someone's pointing out nothing wrong with the challenge, just Binary Ninja might be hiding something important. Yeah, so this is actually a very good, I mean, it might actually be the case because I'm viewing this from like a higher level thing. So if we go down to look at like the actual disassembly, oh, here we actually have this stuff reappearing. So actually what I said before was incorrect. It wasn't the compiler that optimized the statements away. It was in fact the decompiler. So if we switch back to the disassembly, you can see this printout of admin, which we don't have here in the high level overview. So in this case, the decompiler or the high level IL is kind of too helpful. It's removing what it thinks is unnecessary detail, but here it's actually very relevant details. So let's look at it like this. But disassembly. So this is like a graph view of the program, but just the disassembly of it. And here we see that this is the 7th case of the switch thing. And here we have a compare against 0, which will say you're not admin or show the admin menu. And it's actually using this offset RBP -4. So this is this variable C. And here it's actually initializing this to this 99999 value. So the question is, where is this then relative to the other buffer? So where is the fgets? Is this choice buffer, which is located, actually, let me zoom in a bit so that you can more easily see the text. So it's located here at RBP -C. So this actually means that the choice buffer is before this ID buffer, which means that my original idea works absolutely fine. So RBP is the register which contains like the base pointer for the frame. So the memory layout will be like the choice buffer here, 8 bytes, and this is at RBP minus 12. And then you will have, so this is 8 bytes, and then you have here at RBP minus 4, you have this ID, which takes up 4 bytes. Maybe listing it like this. So this means that we can overflow from the choice buffer into the ID buffer. So now we can just easily then modify our payload script here to the first thing we want to do. And this also means that my menu, my abstraction thing here is actually too high level, because we don't want to send just like a number. We want to send a certain number of bytes. And specifically, let's so there's a question if RBP stands for the location of the return address in memory. Not really. It's a BP is base pointer. So every function call sets up what's called a frame, and the frame will contain the stored return address, the stored previous base pointer, and all the local variables. So the base pointer will typically point actually to the location of the previous base pointer, I think. And then you have the return address, if memory serves me correctly. But that's actually not important here. So we should be able to just then overwrite this by waiting for the menu prompt, and then we should be able to send so first we can send like 8 zeros. So the question was, why are we going down from RBP minus 12 minus 4? Yeah, so the way the stack, so the stack is a stack data structure. You mean you push things on top of the stack and you pop things from the top of the stack and so on. But the way the stack grows and shrinks in memory is opposite to the address order. So pushing something, the stack grows downwards. So by pushing something onto the stack, you put an item at a lower address than so that you have the stack pointer, which is pointing to the top of the stack. And when you push something to the stack, you decrease the stack pointer and you put something at a lower address. So essentially, you could think of it as the after the initial like stack setup, you will push the ID, or like you will push the space that's needed for the ID variable onto the stack. So this means basically we would like decrement the stack pointer by 4 to just conceptually make room for this, and then you would do another 8 bytes for the choice variable. And so what we want to do now is we want to overflow this choice buffer. So first we just send 8 characters of whatever, and then we want to send 4 bytes. We want to send the value 0. So here we can use this pack32. So we take 0 and pack it as a 32-bit little engine integer. So this will just be 4 null bytes in practice. Also, let's check that this will not cause an issue. So we have the menu. Sorry, the menu, and then Okay, let's try this. This might not work. Just set an interactive thing here. And let's go back to running this locally. Oh, it did work. So as I described, we send a few characters of whatever, and then this these 4 null bytes, and then this will then overwrite. So it will overflow the choice buffer and then set this to 0, and the admin choice will work and print the flag. So let's just move this to, you can actually move this to the end of the exploit here. And you can run this these both, and you could do then just process to get one flag and admin to get the other flag. And then just to make it even more we just implement this directly in Pwnes just because it's fun. So if we see we receive one line with that, and then the next one is flag 1, and then we do menu option 8. Oh, sorry, that was, yeah. And we just print these to make it all nice and clean. And I did something incorrectly because that didn't work. I mean, we already solved the challenge, but I think it's nice to just clean this up. Oh, I mixed up the 2 messages that we were looking for. Yeah, okay, cool. So now we have a nice script that will just get both of the flags. We can even do some nice like decoding this into proper string and strip it like this. And now let's just switch this to run this against the remote thing. And we get this other flag as well. Wow. And I actually technically mixed up the names of the flags because we're getting number 2 before number 1 now. But yeah, okay, so that's how you solve these 2 challenges. I don't know, any questions or comments from anyone in the chat? How are you all doing? Are you still awake despite all my ramblings? I also like to just copy the output of the script into the solution to kind of like see that it worked, and then we can close this down. So let's close binary linear. So question if I plan on streaming regularly. Yeah, so I have been having this idea that I should start doing this more regularly. I was thinking maybe, you know, maybe once a week or maybe once every other week or something, to get some kind of a consistency going. And previously I've tended to do kind of long sessions and not very often, but I was maybe planning on doing it maybe more regularly, but maybe not quite as long sessions. So let's look at something else then. I think we could do so we have like any requests. We have this like 5-part forensics challenge. Not sure if that's a great idea. Some Pcap analysis, reversing and web with only 6 solvers. That seems kind of interesting, actually. So there's a question if I only do binary reversion. No, I don't. Not at all. I can basically do any category. So AIMLES is a good one. Okay, let's go for this. We have some forensics, some crypto, and disobeyed. It's the it's a conference, right, in Finland. And so Nixu is a Finnish company. So they, I think there's a big overlap between the communities here. So I think it's related to this conference or hackathon or LAN party or you know what it is. This channel was part of the Disobey 2019 CTF. AIMLES is going public soon, and they are preparing for a final security audit. Their local OPSEC DevSec op guy went through the systems before the real auditors arrive, and some things may be indeed to be corrected. We managed to get a hold of some traffic in that network, see if you can do some pro bono. Okay, so we have this pre-audit Pcap. So it's like AIMLES, yeah. And then we create a directory. So pre-audit. And this is a Pcap file, so it's a network recording. So the first thing we want to do with this is open it in Wireshark. And while it's doing that, there was a question. New to this hacking thing, the previous programmer just wanted to know what keeps you going. I'm just scared of that infinite knowledge. So, I mean, first of all, my knowledge is absolutely not infinite. There are a lot of people who are way more knowledgeable than me. But yes, thank you. I think it's just interesting. I mean, I've been doing security stuff for like, it's not that long, but it's getting a little bit longer, like maybe like 8 years or something now. So before that, I've been programming since I was, I don't know, like 7 years old or something, but that doesn't, you know, really matter. You can have been doing that for a little bit or a little bit more, but I strongly suggest, like, if you want to get good at security stuff, that you get good at programming. That's like a strong recommendation for me. Like, some people say that, yeah, you can do IT security without knowing programming, and like, I mean, that's kind of maybe true a little bit in some cases, but I think like to be really efficient at the technical aspects of IT security, you really should know programming to a decent level. So it's especially you want to be good at reading code. But as you saw, it's also nice to be able to just quickly write a Python script that will automate some task for you or something like that. But so you need to be able to write, at a good level in maybe like, one or two languages or so. And then you should be able to read a lot of different languages. That's very useful. So yeah, if you have any other questions, like how about things like that, please post them in the chat. For now, let's look at the Pcap file. So something I like to do is first just to have like a simple like scroll through. We see that there's some SSH traffic going on. Some other stuff, just a quick scroll, and then to kind of like confirm that because sometimes you will get like a huge Pcap and it will have like a lot of one part of traffic and it feels like that's the only thing. But you can go here into protocol hierarchy and you can see that we do in fact have most of the stuff, like 99.7% is TCP traffic, and most of that is SSH traffic. So that's great. And let's look again at this thing. It says forensics and crypto. So this could mean that we need to like break this because SSH is an encrypted data, encrypted protocol. So if we were to like just look at the TCP stream, this I was just gonna say that you shouldn't be able to read this, but there is indeed readable stuff in here. I wonder, is it maybe like somehow negotiating, or did I pick the... Okay, so this needs to be looked into, because for some reason we see unencrypted data going on here, which is very strange. But let's look at what we see. Is first here we see like what do you call it, server banner stuff, and then there's some negotiation going on here regarding which protocol to use, and you see something none here. I mean, that could be multiple things. I don't know the SSH protocol fluently, but it could be the case that they've somehow like negotiated like not encrypting the channel or something. And then we can see that there is like a file listing command being run, and then they're taking this MD5 sum of this TOTP secret, which will be this response, and then so they're doing a bunch of different things here. They are doing check for numbers, and it's basically saying you get the response here, I think, that we have 2 5s and 1 9. So this is kind of like giving us a bit of clues to the contents of this file. And someone here is running they're trying to grep for, so this regex here is making sure that these are the only characters contained in the secret file, because basically they are running this command here. I mean, this I'm just guessing that this is because that's what makes sense. So they search this file for they do grep, and this is like the start of the line, and this is the end of the line, and then we want only these characters. And otherwise, if this fails, it will print vowels are bad, but we don't see that string being transmitted. So probably this didn't print, which means that this succeeded, which means that these are the only characters in the file. And we also see here that it's 8 characters large. So we can put all of these together, and I guess that should be enough to just brute force the contents of this file. Let's kind of like write these notes down. Notes.txt. So we have this TOP secret. It's 8 bytes, and the MD5 hash is this. And oh, this, I was actually close to missing this. Here it's grepping again, and it looks like this is the output of the grep. So you would have 1 4, 2 5s, and 1 9. So this is the output of that. Then we have this. And then we have all of this. So, no, I'm missing the character set. So let's think about how many combinations we have here. We have 8 characters in total. And 4 of them are digits. So the other 4 are not digits. So the other 4 are among these. This is 20 characters. So we have 20 to the power of 4 different possible combinations for the characters. And then for the numbers, we know that it will be 1 4, 2 5s, and 1 9. So that means that, well, we can just double count and say that it's 4 digits that we know, and we can order them in any order, which would be 4 times 3 times 2 times 1. Now there's some double counting in here because swapping the places of the 5s won't make a difference, but the combinatorics are much easier. Also, I'm going to copy this into Python. So changing this to this. So I don't think this is that big of a number. It's like 4 million. Yeah, we can easily brute force this. So let's write a script for this. We need hashlib, and we need iter tools, and we need to copy over those characters, and we need the target MD5 sum. So now what we want to do is we want to just like brute force through all of these combination and check for this valid thing. So, oh, actually, I'm not taking into account here that we don't know the position of these right. So maybe we should be a bit smart about this, because there will be some other factors multiplied on top of this. But maybe that's fine. How many? What's the smartest way to brute force this? Because the number of permutations, all of this is 40,000. So that puts us at like a bunch of billions of possible combinations. Hmm. Let's see. So it would be nice if I could avoid using like a real hash cracking tool like Hashcat or something. If we could just do this simply in Python, if it was quick enough. But now I'm a little bit worried. So let's go to Wolfram Alpha. And what is H choose 4? That's just 70. Okay, so that might actually be fine. So the whole thing is basically then that we have, think of this, we have kind of like 8 empty slots for the characters that we want to fill out. And then we know that half of them are digits, half of them are characters. So first we select what combination of characters to try. And for this, there are, of course, 20 to the power of 4 different combinations because we can have duplicates and so on. So let's say we choose like JKLM. Then we need to place them into these different positions. And we could do this in, I guess, like for the first one, we have like 8 different choices, and then we have 7 different choices, and 6 choices, and then 5 choices. But yeah, that will be fine. And then we fill in the digits. So do we have this in tools? We want the combinations. Yes. So first of all, we want the letters, which will be just the product repeated 4 times. So this will generate, I'll just print the first one and break. Oh, this thing here is 33 characters, which doesn't make sense. So I think this 0 here should go, because this seems to be the correct output. So get rid of this. And here you see you get these. And then you do for these positions in tools combination. So from 8 different values, give us 4. I'll just try that this works. Okay, seems good. And then we just need a permutation. Exactly. So digits in the tools permutations, and we have these digits which are 4, 5, 5, 9. So let's just check that this looks fine. Yes, okay, good. So now we assemble all of this. Maybe this is actually going to be really slow. Maybe we should turn into like proper hash cracking thing instead. But let's try it. So we have the, let's call it like parts, which is so we will create this list of all the different characters. We're just gonna put this together and do this. So we create a list with 8 non-entries, and then for each position, we just do we just distribute those letters into those positions. So now I could print this like half-baked thing. So here it would say like we choose the letters B, 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 and we put them in positions 0, 1, 2, 3, and then we will have all of these none things, and we just put those in place. So we could do so we just go through the list again, and if that part is none, then we assign the proper digit, and then we increment this by 1, and then we have a candidate. And it was a comment from source code leader. Hey, just want to say thank you for doing this kind of thing live. Yeah, thanks for watching. So we have this candidate, which is now just joining this together into a string, and then we want to take the hash of this. So first of all, let's just remove all of these print statements. We do hashlib md5 of this candidate, take the digest. So if this is equal to the target md5, then found secret, and the secret is this candidate, and we want to break. Actually, we could print out just this one to just give us some progress. So here I'm doing like a construct in Python where you can do, it might be like, because basically in this break statement, we want to break all the way out here. And you can't really do that in Python, but what you can do is you can do for else. So the else clause of a for loop will be run if there was no break. So what we do here is that we run this for loop. If we don't find anything, then we run continue. So we jump to the next iteration of the outer loop here, or otherwise we break. So we can just repeat this all the way down. So not here. So basically when we find something, it will go like this. It will break here, which will break this inner loop, which means that this part will not be run. So we will go to this break, which will break this loop here. So it will not run this. So we'll break here and we'll go all the way here and exit the program. So if we try to run this, all right, we must encode code ASCII, and then we are still printing the candidate. Not good. So now we see that it's running, and it's not a horrible performance. It's so each time this ticks, we have done 5% of the work. So I should probably you know, do something else while this is running. So now we've done 5% of all the possibilities. So not terrible. Of course, like if you run this with like a proper hash cracking setup, like setting up Hashcat with some proper masking or something, this would probably be much faster. But I thought it was more interesting to just set up these all the set up like the combinations and just run it a simple script like this. So yes, I will not stare at this. I will you know, do something more productive while this is crunching. So yeah, let's have a further look at the contents of the Pcap, because I mean we still don't know what we're using this for at all. I mean, I assume it's for somehow connecting to the server, but so yeah, let's first of all, let's check, can we actually connect? No, this is on a local. So there is someone pointing out it is faster if you do not print it. Yes, that's true, but I also wanted to get some kind of indication of the progress. So like just printing like the outermost loop is one way to get that. Of course, I could do something where it would print less, but yeah, I mean it's not terrible. Here, let's keep it running. So oh, okay. So something, let's back up one step. Let's go back to Wireshark and just clear the filters. So what I did when I was reading this was that I used the follow TCP stream feature in Wireshark, which is very nice. And here we can see I actually picked stream number 1. So there is also stream number 0, which we have not looked at. So here, some of the stuff here is kind of similar, but we also have this pluggable authentication module for TOTP.c. That seems relevant. Let's just copy all of this stuff into our notes. And it was also pointed out that there's a server for in the challenge notes. Okay, so all right, yes, here. This is why you should actually read properly before saying anything. So let's copy this as well to the notes. Go here. So, oh, and here it seems this is part of the code that's being shown. And here is some text that we should read. And right, okay. So first we copy this part, which seems to show part of the code. Let's do this. And then let's read the text here. Actually, just gonna copy this over here. And then copy this part as well here. So first we have to wait, security audit. Considering the security audit in the near future, I did take a quick look on the servers and noticed a few things. Validity duration should definitely not be 5 minutes. That's way too long. Please add it to the roadmap to change it to 30 seconds, especially on production machine. Someone pointed out a security advisor that might apply to our SSH key generation process. Please check it out if it really does, or is it again some academic scaremongering? This link was this. Okay, we should definitely check this out. Please double check that the TOTP secrets of each user are strong enough. For example, do they contain enough different numbers? You can check this by doing what they actually did. And are they long enough, and they're or is their hash trivially broken by searching with Google? This is also something that we should have done, actually, which I didn't. That DevOps specialist who was laid off last month was doing some really wild optimization with the SSH server config. Why do we need a custom compiled SSH client to even connect? Please verify before the auditors flag this too. Okay, this is worrying. And all right, this was just the same text echoed. Or maybe this is just like typing this in and then getting the output back on the connection. So yeah, it's just the same message. Let's delete this. So first of all, did the brute forcing did complete. Nice. But we should still just actually, can we just Google this? All right. This is okay. I usually also go to like Crackstation. They have like big dictionary of, but we do get no match here. But anyway, our code succeeded, and this is the contents of the secret file they have. So that's a step forward. Okay. Um, so can we, first of all, let's see what we're talking about custom client something. Let's see what happens if we actually, no, let's check the security audit. Sorry, the security advisory. The weak keys. Retrieved server credentials from nearly 13 million. One particular large set of weak keys, a Juniper product, poor entropy. So, okay, which was a comment. You missed one character that would have been possible. 7 characters and a new line gives the same result with greps. Oh, so did I get lucky? Let's actually check this. Top secret 1. And then we do we remove one character, we do a new line, or we call this top secret 2, and then we take a look at the grep they were using. So I'll do this on the number 1. It's all fine. Yes, that's true. So now it seems I was like a little bit lucky maybe, but if we really wanted to have exhausted every possibility, then we would have to redo this, but change this value to, well, change all of these to 7, and then just manually add a new line at the end. So but luckily I picked the wrong, picked the correct idea here. So now let's try to actually connect to the server with the regular SSH client. And then port 60.2. So yeah, unable to negotiate, no matching cipher found, their offer none. Okay, so this is why we can read the traffic, because the server wants to use basically like a null cipher to like not encrypt the traffic at all. I wonder if, oh, this is really annoying. Can we like allow this with some flag in SSH or something? SSH allow none. Or do I really have to like? Do I really have to like compile my own? Okay, the attached diff can be applied, specified version of, so that encryption-free SSH client can be built. Oh, okay. So really have to do this? Is that a recent version, by the way? We have like 8.2. Here is some other. You have to make 3 slight modifications to the source code. I don't like this. So here there's like a whole bunch of changes they need to do on that version. Was this posted? It was actually posted fairly recently. Oh, but this is also like a really. Yeah, this is from 2004. It's even older. Let's see if we can find some like simple way to do this without recompiling. Okay, let's see if we can actually compile SSH ourselves. Where do you get the code? So the idea here is that we need to recompile the SSH client to support not encrypting the traffic. I wonder if there's just like because there's like an SSH like Python implementation. I wonder if they support this. Because that would be very nice. Let's just try this, because that would be much simpler than having to recompile everything. So just have a simple, well, I guess we could just do this. Make another script. So this is the server. Username, we don't know yet. And actually, let's just see what happens if we run this. Yeah, incompatible SSH server, no acceptable ciphers. Wonder if they have any support for this in and Paramico. Compression on. It would be very nice if we could just allow this here in preferred ciphers, cipher info. Let me just close a whole bunch of things. And there's also commands apt-get source open SSH. Yes, okay, good. That's how you do this. I very, very rarely do anything like compile stuff from source code, but just let me try if this works. Maybe not. That's unfortunate. So we could just download the source code. For that, you need to add, yeah, I don't have that set up properly, so that's another issue. Yeah, maybe I'll just like prepare this for next time, and this is a good place to take a break anyway. So yeah, we'll do that instead. I will make sure I have like a setup with the OpenSSH code that it compiles, and then I can show how to do that. Since I don't think that's particularly interesting to watch, but basically we need this to be able to connect to the server. And yeah, so we are gonna leave it there for this time. So what we did today was we solved this Pwnel challenge as part of the Nixu challenge, and we started looking at this AIMLES, which is like a crypto and forensics challenge. So yeah, we'll continue some of these soon. And please, if you have any questions or comments, please put them in the chat. And yeah, if you want to know when the next stream is, like follow me on Twitter and like subscribe to the channel here to get notification when the scheduling of the stream is going up. So yeah, thanks for watching. Hope you enjoyed it, and have a nice day. Bye.